Hello and welcome to STAT 441 at Virginia Commonwealth University. This is part 2 of the lecture on probability theory. This is chapter 3 in the textbook. So in the previous lecture, we talked about the idea of an experiment, and then the simplest event that occurs in an experiment is called a simple event. A combination of those simple events can form an event, and then we can describe the probability of an event by adding the probabilities of the simple events. So let's look at an example which uses the idea of events. So here is the experiment. A software engineer must select 3 program modules from among 5 that need to be checked for defective code. If unknown to the engineer, the models vary in the effort required to debug them, what is the probability that A, the engineer selects the 2 modules that require the least amount of effort, and B, the engineer selects the 3 modules that require the most effort? So let's try to understand this experiment. There are 5 codes here, and we pick 3 codes at a time out of these 5 codes. So first we need to figure out what is the sample space, what are the possible combinations of 3 codes that we can pick out of these 5, and then we will figure out what is the individual probabilities of these simple events, and then for the specific cases that we need the probability for. Okay, so since this experiment has 5 modules, we can define these modules by using the symbols M1, M2, M3, M4, and M5. We also know that the effort required to debug them varies. So let's say M1 is the module with the least effort required, M2 is more than that, and then the maximum is M5. So they are in order. Now, to identify the simple events, we have to look at all possible combinations of 3 codes at a time out of 5. So there will be 10 simple events in all, and these simple events are listed here. Okay, so as you can see, the first simple event is that we pick M1, M2, M3, or we could have picked M1, M2, M4, M1, M2, M5, so on and so forth. In this case, the order doesn't matter. So we have 10 possible combinations. Now, all of these combinations, these 10 simple events, they are equally likely. We know that the total probability of the sample space is 1. So each of these 10 events have a probability of 1/10. Okay, now let's look at the specific events that we are interested in. The first event was defined as that we pick the 2 modules with the least amount of effort required. So we will pick the combinations which have M1 and M2. So the 3 combinations with M1 and M2 are M1, M2, M3, M1, M2, M4, and M1, M2, M5. These form the event A. The individual probabilities are 1/10. When we add these 3, we get 3/10. So the probability that the engineer picks the modules with the least effort requiring modules is 3/10. Now the second part, the event B was defined as that we pick the modules which require the most effort. So in this case, it will be M3, M4, and M5, and the probability of this event is 1/10. So probability of B is 1/10. Okay, so these, what we viewed, were events which were simple combination of the simple events. Now we can also look at events which are a combination of 2 or more other events. So such events are called compound events, and we can find the probabilities of these events by figuring out what are the elements in these compound events. So first, let's look at 2 types of compound events. The first type of compound event is A union B, or the union of two events. It works for more than two also, but we'll look at two events here. So when we say union of two events, we mean that and the element will occur in either A or B or both. So any simple outcomes that will occur in A or B or both will be part of A union B. The symbol is A union B, U denoting the sign for union. The other type of event is an intersection event, which is the set of elements which occur in both A and B. So the common elements that occur in both A and B will be A intersection B. Here is the symbol A with the inverted U. B is A intersection B. Okay, so here is the relation between the sample space and the events A and B. So let's say this is the sample space. So this is all possible outcomes. This is event A, this is event B. The overlapping part, the common elements are A intersection B, and then everything in A or B or the intersection is A union B. So this is A intersection, A union B. Then the relations here, S complement is empty because everything is contained in S. S complement will be a blank set or no elements. And similarly, complement of the null set is S. So the signs 0 with the bar across is the null set or no element. Here is what complementary events mean. So when we say complement of an event A, that will be an event that does not have any elements that occur in A. So this will be elements that are not in A but are present in the sample space. So it's written as A complement like this. And then the union of A and A complement. So think about this, all elements that are in A and that are not in A. If we put them together, we get the sample space back. So A union A complement is S. So here is the relation. Probability of A plus probability of A complement is 1. Why? Because A and A complement contains everything that is in the sample space. So therefore, the probability is 1. Also, probability of A will be 1 minus probability of A complement. So just move this here. So 1 minus probability of A complement. Here's an example. Let's say we have the experiment where we toss 2 coins, and we know the sample space for this is 4 elements, HH, HT, TH, and TT. Let's define an event A where at least one head appears. So that has 3 elements, HH, HT, TH. Event B is at least one tail appears. So we have TT, TH, and HT. Let's look at the A intersection B set. A intersection B is elements that are in both A and B. So HT is in both, TH is in both. So HT and TH is A intersection B. Elements in A union B will be elements that are in either A or B or both. So that will be HH, TT, HT, and TH are in both. And that in this case is the sample space, which is not always the case, but in this one, we have all the 4 elements that are present in the sample space. Another thing that can happen is that the intersection of 2 events could be an empty set. They don't have any elements in common. So such events, let's say C and D are mutually exclusive, then C intersection D is blank or empty set. So that's the name for mutually exclusive. Mutually exclusive, this is a Venn diagram that shows that. So if this is our sample space and A and B are mutually exclusive, then there is no overlap between the two. So A intersection B is empty. Okay, another quick example. Let's say the sample space is all numbers from 1 through 10. We have an event A, which is 2, 4, 6, 8, and 10, all even numbers. Event B is 1, 2, 3, 4, and 5, so numbers 1 through 5. So what is A union B? This you can't see this. There's a U union sign here. Combined all elements, so 1, 2, 3, 4, 5 from this, and then 6, 8, and 10 from here. Okay, A intersection B will be just 2 and 4. Those are the two common elements in the two sets. A complement will be anything that is not in A but is present in the sample space. So that will be all odd numbers, 1, 3, 5, 7, and 9. And here's the question, are A and B mutually exclusive? And the answer is no, because it's not a empty set. Okay, here is another example which shows us the relation between union and intersection of two events. So the American Journal of Public Health published a study on unintentional carbon monoxide poisoning of Colorado residents. The source of exposure was determined for 1,000 cases of CO poisoning that occurred during a recent 6-year period. In addition, each case was classified as fatal and non-fatal, and the proportion of these 10 categories are shown here. So in this case, our sample space is these 10 categories, depending on the source and whether it's fatal or not fatal. So fire fatal is one, non-fatal is the second category, auto exhaust fatal, auto exhaust non-fatal, so on and so forth. And these are the probabilities related with these simple events. Now let's define A as our first event, which is carbon monoxide poisoning case is caused by fire. Okay, so there are two simple events here: caused by fire, fatal; caused by fire, non-fatal. And B is carbon monoxide poisoning case is fatal. So all these 5 here will be our event B, and these two are event A. Okay, so we want to find out A union B in this case. So if I list all the 10 events, simple events here, then this is my event A and this is event B. So fire fatal, fire non-fatal, and everything else which is in the fatal category. So when I add these individual probabilities, that gives me the probability of A union B. So fire fatal plus fire non-fatal plus auto fatal plus furnace fatal, appliance fatal plus others fatals. When you add these up, it gives you a probability of 0.245. On the other hand, the probability of A intersection B will be the common elements. So that will be fire fatal. That's the only common element out of events A and B. So that is the intersection of A and B. Okay, so that's all for this lecture. More examples coming up in the next one. Please view the next lecture. Thanks for watching.